Hello class, we're going to talk about integer programming. So far we have learned linear programming. In linear programming, all the objective and constraints functions are in linear forms. And we also require those independent variables to be non-negative. But we have never talked about any integer requirement for those decision variables. So in integer programming, some of the decision variables no longer to be non-negative, but also to be integers. For example, we might require some product must be an integer form because you cannot divide an airplane into 1.5 airplanes like that. You cannot divide a human being into half of the human being either. So integer programming actually is very realistic in our life, especially for those kinds of problems like scheduling workers or manufacturing airplanes, because we cannot divide airplanes or human beings into half. And integer programming basically allows us to build a more realistic model compared to linear programming. Let us try to revisit the case about hot tub problem. In the hot tub case, we are going to maximize 350 times x1 plus 300 x2 subject to three constraints: x1 plus x2 less or equal to 200, 9x1 plus 6x2 less or equal 1566, 12x1 plus 16x2 less or equal 2880. And we also have the non-negative constraints. But in that case, we never specify those hot tub must coming into integers. In reality, of course, we cannot have half of the hot tub, so we must specify them into integers. So suppose right now we are going to require that all the hot tubs must coming in an integers. So we add two more constraints: x1 must be integers, x2 must be integer as well. So that is the only difference from my original linear programming. We have integer constraints. And right now I would like to let you think about the difficulty of these two types of problems. One is the difficulty of solving linear programming and the difficulty of solving integer programming. At a first glance, we thought actually linear programming could be more difficult to solve because we have to solve all those real numbers. We're talking about 1, 1.11, 1.12, 1.13. We have to enumerate on all those different numbers. But for integer, we just go from 1 to 2 to 3. And it looks like integer programming could be easier to solve, right? But actually, it turned out that integer programming is much more difficult to solve. I don't know whether you can recall that. In linear programming, we can find the optimal solution out of those extreme points. And we know that the number of the extreme points actually are very similar to the number of the constraints, so that we can solve the linear programming easily. But in integer programming, we can no longer enumerate on those extreme points because you are subject to the integer constraint as well. And right now, you are not going to touch the feasible area of the last extreme points in terms of the linear programming. Instead, you have to touch on those integer points. And you think about this case. Suppose you have one independent variable numbering from 1 to 1 million, and the other one also numbering from 1 to 1 million. Right now, you no longer have only a handful of the extreme points. Actually, you have 1 million times 1 million points over there. So you try to figure out which integer point will be optimal for you. So you have to enumerate on all those integer points. So integer programming by itself become long polynomial hard problems. It means it's very difficult to solve if you have integer programming, unless you have very specific format and it's easy to be simplified. Otherwise, it takes days, even months or years to solve a big integer programming problem. Due to the complexity of solving integer programming, actually, we are always trying to simplify an integer programming into a linear programming. For example, in a model of maximizing 2x1 plus 3x2 subject to a couple of constraints, like x1 plus 3x2 less or equal 8.25, 2.5x1 plus x2 less or equal 8.75. And we also have long negative constraints for those independent variables, and x1, x2 must be integers. In order to solve this problem in an easy way, we can just remove those integer constraints. We no longer require x1, x2 must be integers, so that actually we can solve the entire problem in a linear programming form. And the linear programming format for this we call LP relaxation for the integer programming problem. Of course, we remove the integer constraints, so it becomes easier to solve the LP relaxation. And to solve the integer programming, actually, we are not going to touch the extreme points of the feasible area. Right now, we are going to touch the integer points of those constraints. For example, in this graph, in the LP relaxation, we touch the outside point, the last point of the feasible area of the linear programming. But suppose we have the integer constraints, we cannot touch that point anymore because that point is long integers. So we have to move the level line down to touch one of the integer point over there. So in terms of the graph approach, it's the same, except that we are touching the last integer points rather than the last extreme points. The procedure is similar to the linear programming. In this case, we can also use graph approach to solve a two decision variables problems. But of course, for a multi-decision variable case, we can no longer use graph approach to solve for that. So one question is, when we have LP relaxation for integer programming, and which problem will give us a better solution? In other words, we are going to have one optimal solution for integer programming, and we are going to have another optimal solution for LP relaxation. And we are asking whether the optimal solution for LP relaxation will be better than the optimal solution for the integer programming. And as we said previously, LP relaxation actually is a simplified form of the integer programming by removing the integer constraints. So remember this, whenever we have more constraints, typically the optimal solution of the more restricted problems will be worse than the problem without such a constraints. So in this case, LP relaxation always have a better optimal solution compared to integer programming. Of course, sometimes they could be tied, but in many situations, when you have integer constraints, your optimal solution and optimal value could be worse off. For a minimization problems, the optimal solution and optimal value of an integer programming will never be below the optimal solution and optimal value of an LP relaxation problem. So as you can see that actually the LP relaxation optimal value will serve as a boundary of the integer programming, depends on whether you have maximization problem or minimization problem. In maximization problems, the optimal value of the LP relaxation will serve as an upper bound, but in a minimization problem, the optimal value of the LP relaxation will serve as a lower bound of the integer programming. Of course, when we're solving for the LP relaxation for the integer programming, we always wondering, can we just round whatever optimal solution we get into integers, and we get the integer solutions, and we can apply them immediately for the integer programming. And actually, this is a very valid concern. If we can do that, we can solve the LP relaxation much quicker, and we can just round it, and it becomes very easy for us, right? But the problem is actually, in many cases, in general, this rounding approach does not work. There's two issues. One, the rounding solution might be infeasible, and even if it is feasible, it might not be optimal. And we have to conquer these two issues. For example, in this graph, if we use LP relaxation to solve the optimal solution, we are going to get the peak point out of this feasible area. If we use the integer programming, we are going to get the point inside the feasible area, and that will be the integer point right below the peak point of the feasible area of the LP relaxation. But if we just route the optimal solution of the LP relaxation, actually we are going to get the point outside of the feasible area on the left-hand side of the peak point. And that point is infeasible. So this just shows us that we cannot simply route any optimal solution of LP relaxation to be the optimal solution of integer programming. In practice, because it's very difficult to solve integer programming, you still want to do routing sometimes. But when can we do that? Typically, if the optimal solution is huge, for example, like you have 1,500,000.5, something like that, and probably it's safe for you to just erase the 0.5 and you just route it. But if your optimal solution is like 2.7, if you route it to 2, it's very risky because 0.2 over 2 is a huge percentage of that, right? And consider the previous case, if we have 0.5 over 2 million, something like that, definitely that's insignificant. So it really depends on what situation you are in and what time is safer to route it. But if you are not sure, just rerun the problem and solve the integer programming to be safe.